Let's return to the simple two-link robot manipulator that we looked at much earlier in the course. And when we first looked at it, we were interested in the kinematics. That's looking at the relationship between the joint angles Q1 and Q2 and the position and orientation of the end effector. Now what we're going to do is to consider that these links have got masses. So I've dropped on the symbols for the center of mass of each of these links. So we think about how this works mechanically in practice. Each link has to support all of the other links that are beyond it. And each link, of course, then is supported by all the links that are before it. So there is mechanically a connection between the links, and the weight of one link has to be borne by the link before it, and the link before that, and so on. Every link then exerts a force and a moment on its neighboring links. So a really useful way to consider the forces and moments that are acting on each of these links is to draw a free body diagram. And what we do is we disconnect the different links and we look at them individually. They are free bodies. Each link has got a mass, and gravity is going to act on that mass with a downward force. The base of the robot is going to provide a vertical upward force to hold the red link up to stop it from falling down. And the green link is going to provide a downward force on the end of the red link due to its own weight. Look now at the green link. There's going to be an upward force here which is equal and opposite to the downward force on the red link. This is Newton's third law. So there's a downward force on the red link, it's the weight of the green link, and there's an upward force on the green link which is provided by the red link to keep it up. Now there is a moment provided by the motor which is driving joint 1. It is providing a torque to stop the red link rotating. And similarly, there's a torque applied to the green link by the joint 2 motor to stop the green link from rotating. And then there is a reaction torque, equal and opposite torque from that motor, which is applied to the red link. So here we see all of the forces and moments that are acting on each of the links of the robot. These forces and moments depend on the pose of each link, depend on the speed of the link and the acceleration of the link, and of course they also depend on gravity. These forces and moments also depend on the link parameters, the actual mass of the link and its inertia and its length and so on. So let's have a look at some of these link parameters. The kinematic parameters we introduced much earlier in the course, and we have the link length. In this case, the length A1 from the axis of joint 1 to the axis of joint 2. And similarly we have the length of link 2. We've introduced link coordinate frames here. Coordinate frame 1 is attached to the end of link 1, and coordinate frame 2 is attached to the coordinate frame of link 2. And we looked at link coordinate frames again much earlier when we were considering serial link manipulator kinematics. We can also describe the position of the center of mass with respect to the link 1 coordinate frame. In this case it is a displacement of C1 in the negative x1 direction. And we also have a mass associated with the link, that's the mass m1. And then we also have an inertia. This is the inertia of the link with respect to its center of mass. And we can do the same thing for link 2, the distance from the link 2 coordinate frame to its center of mass, and the inertia of link 2 with respect to its center of mass. So we have now quite a number of parameters associated with each of the links. For each link we have a mass, we have a center of mass, which in the general case would be a vector described by 3 numbers, and we have an inertia matrix. This is a 3x3 matrix, and if we consider the inertia with respect to the center of mass, that 3x3 matrix is a symmetric matrix. Now a symmetric matrix, instead of having 9 unique elements, has got only 6 unique elements. In total we have 10 parameters to describe the dynamics of each link. We have 1 mass, we have 3 translations to describe the position of the center of mass with respect to the link coordinate frame, and we have 6 unique elements of the symmetric inertia matrix with respect to the center of mass. So for link number 1, those parameters are m1. The center of mass is negative c1 in the x direction. The other 2 elements are 0. The vector r1 describes the position of the center of mass, and in this case it's negative c1, and the y and z components are equal to 0. And we have the inertia matrix, which has only got 1 element, and that is the inertia about the z-axis. Now in this case the z-axis is coming at us out of the page, so we have only 1 finite element, that's I, z, z1. For link 2, it looks somewhat similar. These are the dynamic parameters of each of the links, sometimes referred to as the inertial parameters of the links. When it comes to describing the dynamics of moving bodies, there are a number of different approaches that we can take. One of the most common, of course, is Newton's second law, F equals ma, which relates the force applied to the body to the acceleration that it experiences as a function of its mass. For a rotating body, we can use Euler's equation, which relates the torque applied to its body, given by the symbol tau, to its rotational inertia j, its angular rate omega, and its angular acceleration omega dot. A quite different approach is Lagrange's equation, which relates the kinetic and potential energy of a body to the derivatives of the Lagrangian term, T minus V, and the derivatives of the Lagrangian with respect to the generalized coordinates and the generalized velocities of the bodies in the mechanism. We can use any of these approaches to analyze the dynamics of a serial link manipulator. But in this lecture, we're going to consider the Newton-Euler method. This is a combination of Newton's law to describe translational motion and Euler's equation to describe the rotational motion. A very simple and elegant approach to determining the dynamic motion of a serial link manipulator is what's called the recursive Newton-Euler algorithm. And I'm not going to go into all of the details here. You'll find it in many textbooks. But what I want to do is give you an intuition for how it works. And the first step is to determine the translational and rotational velocity and acceleration for the center of mass of each of the links. We use Newton's law for the translational motion, and we use Euler's equation for the rotational motion. We start at the base of the robot and we work outwards, determining the translational and angular velocity, the center of mass of each link in turn. Once we get to the end of the robot, we then work our way back inwards, and then we determine the force and moment that each link exerts on the link that's closer towards the base of the robot. This method is computationally elegant and very efficient. I'm going to create a 2-link robot in MATLAB. To do that, I'm going to use the toolbox script MDL2Link, and that will create in the MATLAB workspace a robot object called 2Link. This is an object that has a great number of methods and properties, and we'll start to explore some of these. One of the first ones we're going to look at is the plot method. So for the robot object 2Link, I'm going to invoke the plot method, so that's .plot, invokes the plot method on that object, and I'm going to plot it for Q1 equal to 0 and Q2 equal to 0. And here we see the robot manipulator. Now, unlike the one we looked at previously, which operated in the XY plane, we can see that this 2-link robot is operating in the XZ plane. So gravitational acceleration, which is in the Z direction, is acting on the center of mass of each of the links of this robot and will tend to pull it down to make it collapse. And we can use the recursive Newton-Euler equation, and which is the RNE method for recursive Newton-Euler, and I can ask, what are the torques on this robot if the joint angles are both equal to 0? So that's the situation that I've just plotted. And let's say the joints are not moving at all, so they've got 0 velocity each, and the joints are also not accelerating, so they've each got an acceleration of 0. It says that the torque on the first joint, on Q1, that's necessary to hold it in this position is 19.62 Newton meters, and the torque on the second joint is 4.9 Newton meters. This makes intuitive sense to us. The torque on the shoulder joint is going to be greater than the torque on the elbow joint, because the shoulder has to hold up the upper arm and the lower arm, whereas the elbow joint only has to hold up the lower part of the arm. What we don't have a handle on are the signs of these two torques. Which way are they acting? So a good way to see that is to replot the robot using a different option, which is JVEC. What this shows is the axis of rotation of each joint. So if we remember our right-hand rule, in order to understand the direction of a positive torque, what we do is grab the axis with our right hand, point our thumb in the direction of the arrowhead, and curl our fingers around the vector to indicate the direction of positive rotation. And what we can see here then is that a positive torque of 19.6 acting on the shoulder joint is going to be a torque that's trying to lift the robot arm up, which is exactly what we would expect, and similarly for joint 2. So the recursive Newton-Euler algorithm has given us the torques that are required for the robot to stay in this particular configuration with both its joint angles equal to 0, and with 0 joint velocity and with 0 joint acceleration. These are the torques that are required for the robot to be in this configuration and not move.